तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Good morning. So, up to now in this course we have been discussing silicon based devices, that is bipolar logic families as well as MOS based logic families and different circuits. Well, when we talked about bipolar logic families, we also made reference to heterojunction bipolar transistors, which were made using compound semiconductors. But in those devices the circuits were not modified by the introduction of gallium arsenide devices, in the sense that the same circuits in the same circuits one could replace the silicon bipolar transistor with a heterojunction bipolar transistor. The circuit did not change. Well, in this case, what we are going to discuss now in today's class is some circuits which are specific to certain devices made using gallium arsenide. Before we actually go into the devices, let us look at some of the properties of silicon and gallium arsenide and see why we would prefer gallium arsenide for these applications, and what are the device or which device we take for this type of logic circuits. Okay, so if you look at the properties, if you take gallium arsenide, silicon. Okay, first let us take a look at the band gap. For gallium arsenide, the band gap is 1.42 electron volt, and it is a direct band gap material, whereas for silicon it is 1.1 electron volt and it is an indirect band gap material. Okay, the direct band gap material, as you know, that it means that the conduction band minima and the valence band maxima are both at the same momentum. So, one can use it for optoelectronic devices. So, gallium arsenide can be used for optoelectronic devices, but since silicon is an indirect band gap material, it cannot be used for optoelectronic devices. So, that is a disadvantage of silicon. So, in nowadays a lot of optoelectronic integrated circuits are being fabricated, where you have both the signal processing circuitry as well as the sensor, optical sensor in the same chip. So, for that purpose gallium arsenide would obviously be an advantage. The band gap of gallium arsenide is higher than that of silicon. One advantage of that is that gallium arsenide can be used at higher temperatures, which is an advantage for gallium arsenide with respect to silicon. Of course, one disadvantage is if you have a higher band gap material, it is difficult to make ohmic contacts, but that has been overcome through improved technology. Okay. But the most important difference between gallium arsenide and silicon is in the nature of their drift velocity electric field characteristics. If one looks at this velocity versus electric field characteristics for electrons in gallium arsenide and silicon, we will observe that in silicon the drift velocity for electrons follows a curve something like this, whereas for gallium arsenide it is the nature of the curve is something like this. Okay, which means that if the slope is higher initially, which means that the for gallium arsenide, this is for gallium arsenide, this is for silicon, which means that the mobilities, the low field mobilities in gallium arsenide is higher than that in silicon. Okay. So, if we write the low field mobilities in this table, okay. For gallium arsenide, the low field mobility is around say for 10 to the power 7 doping of electrons. Okay. Mentioned here for electrons, this is around 5000 centimeter square per volt second. For Nd is equal to 10 to the power 17 per centimeter cube. Okay, and it can go right up to 8000 centimeters squared per volt second for undoped gallium arsenide. Whereas, if we look at the silicon mobilities, well, it is around, it would be around 800 centimeters squared per volt second for Nd equal to 10 to the power 17 per centimeter cube. So, we see a distinct advantage for using gallium arsenide, that is, it has got a very much higher low field electron mobility compared to silicon. Okay. I have also put down the undoped the mobility for undoped samples, because now we also have devices like the high electron mobility transistor using gallium arsenide, where the electrons, or where the current where the electrons actually flow in the undoped part of gallium arsenide, giving rise to such high mobilities. That is why it is called a high electron mobility transistor, HEMT. So, so we see that this is the advantage which is utilized in making very fast logic circuits, okay, the low field mobility. Okay, but what about the saturation velocity? Of electrons? Well, for both of them, it is of the order of 10 to the power 7 centimeter per second. This is also of the order of 10 to the power 7 centimeter per second. But the point is, because the initial low field mobility is higher for gallium arsenide, this saturation velocity is reached at a much lower electric field in gallium arsenide. If we come back to this curve again, we see that the saturation velocity of silicon is reached. This is around 3 into 10 to the power 4 volt per centimeter, whereas for gallium arsenide, okay, this saturation velocity, okay, above this electric field, okay, this velocity will always be greater than the saturation velocity. This field is much lower. It is in fact, even at electric fields of the order of 10 to the power 3 centimeters volt per centimeter, you have very high, you have velocities equal to the saturation velocity. So, the point is that in order to reach saturation velocity, you require lower electric field in gallium arsenide, and lower electric fields means lower voltages applied across the device, which means that the devices can be operated at lower voltages, and if we can operate a device at lower voltage, it means you require less power. So, that is a distinct advantage for gallium arsenide devices. Also, since the saturation velocity is reached at a lower electric field, when you have a field effect transistor, the carriers in major portion of the channel will be traveling at saturation velocity in gallium arsenide devices, while in silicon devices, the carriers only very close to the drain end may be traveling at saturation velocities. So, that is a distinct, also a distinct advantage for gallium arsenide devices. Okay. Then of course, peak velocity, okay, for gallium arsenide we see that we have a peak velocity of okay, which is around 2 into 10 to the power 7 per centimeter per second. which we do not have for silicon devices. In fact, this can also be utilized if we properly design the device to achieve very high speed devices. All right. So, we see that if we have a sort of n channel device where the carriers are electrons, gallium arsenide has a distinct advantage over silicon in terms of speed, and this can be utilized to realize devices of higher speed. But if we look at the hole mobilities, low field hole mobilities, okay, this is for gallium arsenide, it is around 250 centimeters squared per volt second, whereas this would be around 300 centimeters squared per volt second, again for doping concentration of 10 to the power 17. So, it shows that the hole mobility is very poor in gallium arsenide. So, this gallium arsenide cannot be used to make complementary devices like CMOS as we in silicon devices, as we do in silicon. So, that is a distinct disadvantage also for gallium arsenide devices. So, we have to make circuits which use only n channel devices. So, so we will have to look at such circuits only. We cannot have complementary circuits. Okay. So, these are some of the differences. Now, let us look at some more property differences between the two. Okay. So, just substrate resistivity. That is, these gallium arsenide devices can be made on undoped gallium arsenide samples. In fact, they can be not only undoped, but by introducing certain deep level impurities, the resistivity of the sample can be increased very heavily. For example, you can have samples having resistivities of 10 to the power 6 to 10 to the power 8 ohm centimeter, whereas in silicon this is low. Okay. Now, usually most gallium arsenide devices would be made on these type of substrates which are called semi-insulating substrates, and the advantage is this semi-insulating substrate can be used to isolate individual devices. Not only that, since they are made on this high resistivity substrates, the parasitic capacitance from the device to the substrate is very, very low, and because of this reduction in parasitic capacitances, the device can be operated at higher frequencies. Okay. So, this the parasitic device to substrate capacitance can be almost eliminated. Okay. So, that is a distinct advantage again for gallium arsenide. Okay. Now, there are some disadvantages too, which we shall come to. Okay. Then one is the surface states. The surface states are the unsaturated dangling bonds at the surface of a material, and because of that, what you have is when you make a device, you have that gives rise to some surface charges. Okay. And these surface charges play a role also in device operation. Now, this surface states densities are of the order of almost 10 to the power 12 in this is per centimeter squared electron volt in gallium arsenide, where this maybe is quite low in silicon, about 10 to the power 10 per centimeter squared electron. Now, the effect of this surface states is that in gallium arsenide, number one, it is difficult to make ohmic contacts, because they result in what you have is you have what is called Fermi level pinning, that the Fermi level is pinned at one particular level at the surface when you make a metal contact. But so ohmic contacts have been made using heavily doped substrates. So, if you make the metal contact on a heavily doped gallium arsenide substrate, you do get ohmic contact. So, that can be overcome this way. But the other problem is that because of this Fermi level pinning, one cannot really have inversion layers in gallium arsenide substrates, just like you have in a MOS in a semiconductor in a silicon device, silicon MOSFET, because so you cannot have a MOSFET as such. It's very difficult to make a MOSFET on gallium arsenide because it is very difficult to invert the surface. Okay, so you cannot do that. So, you cannot have this enhancement type of devices, MOSFETs, as you have in silicon. Okay, that is one problem. Okay, and so we cannot have really MOSFET type of devices on gallium arsenide. Okay, another problem, of course, is that if you look at a MOSFET, you require what is called an oxide, okay, MOS structure, metal oxide semiconductor. You require a native oxide. Now, gallium arsenide native oxide is very unstable. It cannot be used for any practical devices, whereas for silicon, it is very, very stable. And in fact, the thermally grown oxide is used as the for making MOSFETs in silicon devices, whereas that is not possible in the case of gallium arsenide. So, you see that these, because of these two properties, that is large number of surface states and the native oxide problem, we cannot have MOSFET type of devices in gallium arsenide. So, although n channel field effect transistors would be quite attractive for gallium arsenide because of the advantages with respect to mobilities, we cannot make MOSFET type of devices in gallium arsenide. So, the device which is used for making in gallium arsenide for integrated circuits is the MESFET and not the MOSFET. Which is also a field effect transistor, but in that case we do not have a MOS structure as in a MOSFET, but we have a metal semiconductor junction. Okay. So, we shall now take up this particular device, we shall look at the different properties of this device, and then we shall see how these devices can be used to make integrated circuits. Okay. So, we shall now take up this particular device, the MESFET, for making integrated circuits. These devices are quite typical of gallium arsenide. In fact, one can really make MESFETs in silicon, but nobody would make it because the MOSFET is a much better device. Okay. But since in gallium arsenide we cannot make MOSFETs, we have to go for this MESFET type of devices. Now, let us see how a MESFET actually looks like. Well, there are two ways basically in which a MESFET can be made. In one case, we start with semi-insulating gallium arsenide, and then a shallow implant of n-type implant, which is silicon, which is an n-type impurity in gallium arsenide, can be made, n minus I call it. This is a lightly doped n-type implant in gallium arsenide at the surface, and then we make a heavy dose of implant, implant of a higher dose, which we call n plus. Okay. This is to make the ohmic contacts. Okay. As we have already said that we require heavy doping, okay, in order to make ohmic contact. Now, this is lightly doped region, this is the heavily doped region. So, when you make a metal semiconductor junction, okay, this region is going to result in a Schottky diode, okay, whereas in the heavily doped regions it is going to make an ohmic contact. So, you have the metal here, you have a metal here, and you have a metal here. Okay. So, this is the source, this is the drain, and this is the gate. the difference between the MESFET and the MOSFET, as you can see, in a MOSFET you have an MOS structure, metal oxide semiconductor structure, whereas here you have a metal semiconductor structure. So, this metal semiconductor forms a junction, okay, just like this is quite similar to a JFET, junction FET, where you actually have a PN junction, whereas here you have a metal semiconductor junction, and it is this metal semiconductor junction which will control the flow of current from the flow of carriers, electrons in this case, from the source to the drain. Okay. This can also be, the same device can also be made using an epitaxial wafer, in which the starting material is, you have a semi insulating gallium arsenide, on which a lightly doped N gallium arsenide, and on top of which you have heavily doped N gallium arsenide. Okay. Now, what is done is, first what is done is recess etching is done on the surface. So, this region is etched down to reach this N gallium arsenide. Okay. So, you have N plus here, whereas N is here. So, now what is done is the metal contact here, metal contact here, and metal contact here. Again you have the source, gate, and the drain. Okay. So, this is the channel region, this is the gate on N minus, this is going to be Schottky contact, whereas this metal on N plus is going to be ohmic, these two are going to be ohmic. So, this is also a MESFET structure. This can be done using some already grown epitaxial wafers, where you do not have to carry out the implantations. So, now let us see how this device operates. So, that is the next thing which we are going to take up, and look at the characteristics of this particular device. Okay. Now, this metal semiconductor junction behaves almost like a PN junction or a P plus N junction. This metal N junction is going to behave as a single sided abrupt PN junction, that is P plus N junction. So, there will be a built in potential VBI. Okay, there is going to be a built in potential VBI just like any PN junction, and because of this built in potential, there is going to be a depletion layer here on the N side. Okay, and say let us suppose this built in potential is like this. Now, this depletion width, so there is a depletion layer of a particular width. The width of the depletion layer, say W, can be related to the built in potential. By solving Poisson's equation we can get it. Okay. So, VBI is equal to Qn W squared by twice epsilon. Okay, or alternately we can write W is equal to twice epsilon silicon VBI by Qn, where N is the doping concentration, epsilon is of course the permittivity, and VBI is the built in potential, Q is the electronic charge. Okay. Now, so this is the depletion width which exists normally in the device. Now, if T is the thickness of this N layer and if T is greater than W, that means there is still a part of the channel which is undepleted. Okay, and that means that if you now apply a voltage between the drain and source, a current can flow between the source, between the drain and source, electrons can flow, there is a channel existing for current to flow. So, it is a normally on device. Okay. So, we call this the normally on device, okay, or it is also called a depletion mode device. Okay. On the other hand, if T is less than W, which means that if the built-in potential is sufficient, the depletion width due to the built-in potential is much larger than the thickness of the channel. That means, at 0 bias, okay, without applying any bias, the depletion width is completely going to cover the channel. So, there is no way a current can flow between the source and the drain. So, if T is less than W, then the device is going to be normally off, and this is called a enhancement mode device. Okay. Now, for these devices, just in the case of MOSFET, we also define what is called a threshold voltage. The threshold voltage is that particular gate to source voltage at which the current there is conduction just begins, okay. That is, if the gate to source voltage is greater than the threshold voltage, there is conduction, but if the gate to source voltage is less than the threshold voltage, there is not going to be any conduction. That is the gate to source voltage at which the depletion width is just covers the channel region, the thickness T, okay. Now, if T is greater than W, that means it is not fully depleted. So, what we have to do is we have to reverse bias the gate junction, okay. This junction we have to reverse bias it more to deplete the entire channel. So, that is, we must apply a negative gate voltage to make it so that the depletion width just covers the complete channel. So, for a depletion mode MOSFET, okay, where T is greater than W, the threshold voltage is going to be negative, okay. Whereas, for enhancement mode MOSFET, since the depletion width due to the built-in potential is greater than the channel length, we in fact have to forward bias the gate voltage, that is, we have to apply a positive gate voltage, so that the depletion width just is just enough to cover the channel region T, thickness T. So, for T is greater than W, a depletion mode device, Vt is going to be negative, and for an enhancement mode device, Vt is going to be positive. Okay. So, for that what we do is we define what is called a pinch off voltage, VPO, which is the voltage across the depletion region just sufficient to for the depletion region to just cover that thickness of the channel region T. Okay. So, VPO will be Qn T squared by twice epsilon. Okay. And the threshold voltage Vt of this device will be given by Vbi minus Vpo. That is the extra voltage which is required to pinch off the whole channel. Okay. So, the threshold voltage is given by this. Again, as I said, we can have two types of devices. One is the enhancement mode device, which is a normally off device, and depletion mode device, which is a normally on device. Now, if you want to make, it is very clear that if you want to make enhancement type device, since the depletion width due to the built-in potential should cover the entire channel, the channel thickness T should be made quite small. So, for this type of device, T less than W, T should be made very small, or the ND or N, the doping concentration should be made also could also be made small, so that for the same built-in potential, if you come to this expression, okay, for the same built-in potential, if N is small, W will be large. So, either we can make T small or W large by making N small. So, if we want to make an enhancement mode device, we have to make T small or N small, the doping concentration small. If we want to make a depletion mode device, we can make the thickness large or the doping concentration large, so that W is small. So, normally it is easier to fabricate depletion mode devices, okay, than enhancement mode devices, because you require much greater control in making enhancement mode devices. Okay. Now, let us see how what is the characteristic of these devices, that is the current voltage characteristics, how the nature of these characteristics, okay, for these devices. So, you have the drain current on one side and the drain to source voltage on the other. Okay. Now, suppose we have again a depletion mode device, okay, where the threshold voltage is negative, and at this point, say at 0 bias, the gate voltage, the channel already exists, or whatever is the bias, if at a particular bias the channel exists, okay, where current can flow. That is, the channel is that is the entire region here is not fully, the region is not fully depleted. Now, if we apply a drain to source voltage, current can flow in this path, okay, and the current will be given by, if we write I is can be given as A, Q, and V, where A is the area, cross sectional area of current flow, Q is the electronic charge, N is the concentration of carriers, okay. N is the electron concentration, which can be said to be almost equal to capital N, which is the doping concentration, and V is the velocity. So, it is almost equal to A Q and V. V is the velocity of the carriers. Okay. Now, when we apply a, so this basically behaves like a resistance, all right, this basically behaves as a resistance, and if we apply a drain to source voltage at a particular gate to source voltage, then as we increase the drain to source voltage, the current is going to rise linearly initially. But as we are increasing the drain to source voltage, the drain voltage, the voltage at the drain end of the channel is increasing, which means, and this voltage is in such a direction as to reverse bias the this gate to substrate semiconductor junction at this end. So, the depletion width is going to keep widening at the drain end, all right. There is going to be a widening of the depletion width at the drain end. Now, since there is a widening of the depletion width at the drain end, it means that if you look at this expression here, I is equal to A, Q, N, V, which means that A, that is the cross sectional area of current flow, reduces. Now, if we must have a constant current flowing, okay, along throughout the channel, which means that the basically what is going to happen is the velocity, if this A reduces, velocity has to keep increasing. Okay. This is done, this happens because electric field also at the drain end keeps increasing. Okay. The electric field is not constant throughout the channel along the current flow, but the electric field is higher at the drain end, which makes the velocity increase. But we know that if we keep on increasing the velocity, ultimately it will reach saturation. Okay. So, basically what happens is, initially if as we keep on increasing the drain to source voltage, because of the reduction in the cross section area, the current actually does not rise linearly, but sort of sublinearly, okay. And finally, when the velocity reaches the saturation, the current also saturates, okay, and it becomes something like this, okay, all right. There is a slight increase in current, because once after velocity saturation is reached, if we keep on increasing the drain voltage, okay, the velocity saturation point actually moves towards the source end. So, which effectively means which means an effective reduction in the channel length, and so a slight increase in current. So, this is for a particular gate voltage. If we take a higher gate voltage, more positive gate voltage, the current is going to increase more, because for a higher gate to source voltage, the depletion width in the channel is going to be less, but the initial cross sectional area of current flow is going to be more. So, this is the nature of characteristics which you have. So, for different gate to source voltages. So, in fact, this nature of characteristics is valid for both enhancement as well as depletion mode devices. Okay. So, if we have a depletion mode devices, it means that the current flow will exist even when VGS is less than 0 volts. Okay. For example, if the threshold voltage of a depletion mode device is minus 1 volt, then you can have current at minus 0.9, this could be minus 0.8, this could be minus 0.7, minus 0.6, minus 0.5. Okay. So, as we are making the gate voltage approach 0, the current increases. If it is an enhancement mode device with a threshold voltage say 0.1 volt, okay, then this could be for 0.1 volt, this could be for 0.2 volt, this could be for 0.3, 0.4, 0.5. So, this is basically for increasing VGS. All right. So, this is the nature of characteristic. We see that the nature of characteristics is almost is quite similar to that of a MOSFET. Okay. And okay. So, now this current in gallium arsenide devices MESFETs, okay, we can in fact use the same relations for MOSFET, but one particular model which is generally used for the current voltage characteristics is what is called the Curtis model, where the expression for drain current is given as ID is equal to beta VGS minus VT squared. This is similar to the square law in MOSFETs, okay, beta VGS minus VT squared, then you have 1 plus lambda VDS. This is to take into account the increase in current after saturation. Okay, this all right. This is also quite similar as in a MOSFET, but then you have a term tan hyperbolic alpha VDS. Okay, the tan hyperbolic is used as the argument of this alpha VDS is small. Okay, when alpha VDS is small, that means when VDS is small, tan hyperbolic alpha VDS would be almost equal to alpha VDS, which means that as VDS increases, tan hyperbolic alpha VDS would also increase almost linearly. So, this current would increase almost linearly, but when tan hyperbolic alpha VDS becomes large, okay, then this function approaches unity. Okay. So, tan hyperbolic alpha VDS is going to become 1, which means this we get this value beta VGS minus VT square into 1 plus lambda VDS, which is saturation current as in a MOSFET. All right. So, the advantage here is that we can use a single expression to express the entire current voltage characteristics, unlike in the square law models of MOSFETs, where you have one expression for the linear region and another expression for the saturation region, and then makes it very simple for simulation purposes. And if is equal to 0, so this is for VGS greater than VT, and this is equal to 0 for VGS less than equal to VT. So, this is the drain current model for the MESFET. So, this models this current voltage characteristics. Okay. All right. Then a little bit on the equivalent circuit of MESFETs. Okay. This is the MESFET equivalent circuit, the large signal equivalent circuit. We can have what we have is a current source, okay, ID, and this is given by this relation. Okay, this is given by the relation of ID here, and so this is the drain point and this is the source point. Okay, and from the gate you actually have, if you look at this, you have a Schottky contact here. So, a current can flow, this is a Schottky contact, and you know that a characteristics of a Schottky diode, that is it is just like a p-n junction diode. So, once the gate this voltage exceeds the cut in voltage, there is going to be conduction. So, basically you have two diodes, okay, these are Schottky diodes basically, and okay, between the gate and the drain as well as from the gate to the source. Okay. And so, these diodes will in fact start conducting once this it exceeds the cut in voltage of these diodes. So, there will be a gate conduction unlike a MOSFET, this is quite unlike in the MOSFET. So, this also because of the presence of these diodes, it is also going to clamp the gate to source voltage to a particular value, that is the cut in voltages of these diodes normally in gallium arsenide devices around 0.7 volts, which means that the gate to source voltage or the gate to drain voltage cannot exceed that value, okay, because once it approaches that value, there is going to be a conduction of these diodes and the current will be limited. Okay. So, you also have two other elements, the capacitances, okay, between the gate to source and the gate to drain. Okay, these are, this is expressed as CGD and CGS. These are basically the junction capacitance type. This is due to the depletion widths at the gate and the drain ends, at the source and the drain ends of the channel. Okay, and these can be expressed as CGD can be given as CGO 1 minus VGD Bi to the power half, okay, and CGS is equal to CGO 1 minus VGS by VBI to the power half. Now, when this means what is CGO? That is when VGD is equal to 0, CGD is equal to CGO, and when VGS is equal to 0, CGS is equal to CGO. So, the CGO is actually the capacitance at 0 bias, okay, and is given by CGO is equal to epsilon W by L, okay, that is epsilon into area by twice W, okay, sorry, this well, this is the width of the device, okay, whereas this epsilon W is the width of the device, L is the length of the device. So, twice I shall use another symbol, say D, where D is actually the depletion width at 0 bias, okay. D is the depletion width at 0 bias, and D is why do we put this 2 here? Because we are partitioning the total charge in the depletion layer between the source and the drain, okay. So, CGO is actually epsilon A by D, the depletion width, by 2, because half of the CGO is for the gate to source and half for the gate to drain, and this D is nothing but the depletion width due to VBI, that is depletion width the VBI, okay. So, this is twice epsilon VBI by Qn, okay. So, that gives us the the large signal model of the MESFET. You of course can have drain and source resistances RD and RS. So, then this will become the internal source point, this one will become the internal drain point. So, you have the RS, so this is the external source point and this is the external drain point. So, you have RD and RS. So, in which case the internal gate to source voltage VGSI will be equal to the external gate to source voltage minus ID into RS, ID into RS, and the internal gate to drain voltage VGDI will be equal to the external gate to drain voltage minus ID into RS plus RD. Okay. So, the internal gate to drain voltage is equal to external gate to drain voltage minus ID into RS plus RD. This actually, so this is the internal drain to source voltage. Sorry, this is the internal drain to source voltage. This is the external drain to source voltage. VDSI, the internal drain to source voltage, is equal to the external drain to source voltage minus the drop across these two resistors. VDSI is equal to VDS minus ID into RS plus RD, whereas the internal gate to source voltage, which is between these 2 points, is the external gate to source voltage minus the drop across this RS. Okay. So, what we have to do in actual practice, if the source and drain resistances are important, we have to go to this current expression here, and we have to replace the gate to source voltage and the drain to source voltage by the internal values. Okay. That is VGSI instead of VGS, because the currents will be related to the internal values. Okay. So, this is the large signal model of the MESFET. Okay. For the small signal model of the MESFET, what we have is from, if we take the small signal model, from the drain to source, we have a current GM-VGS. Okay. The drain, the current is dependent on the gate to source voltage and the drain to source voltage. So, we have a current source between drain and source given by GM-VGS, where GM is equal to del ID del VGS. Okay. You have drain resistance RD, where RD is equal to del ID del VDS. Okay. And then you have the two capacitances, gate to source and gate to drain. So, you have CGS and CGD, which we have already seen. So, this is the small signal equivalent circuit of the MESFET. Okay. So, in today's class, what we have done is we have looked at the MESFET device in quite detail, and what we shall do in the next class is we shall take this device and see how we can make different circuits, okay, digital circuits which can be used. Okay. Now, of course, the circuit is going to be different from the MOSFET circuits, because of the one primary difference is that in the MESFET you have this there can be gate conduction, whereas in the MOSFETs we are not having, and this limits the gate to source voltage. So, so for this the circuits are going to be quite different. So, in the next class we shall take up the MESFET circuits, okay, for the high speed digital integrated circuits. Thank you.